Hi everyone. This is about the INE 504 project and presentation, which focusing on solar cell. So for this project, 3 journals actually has been selected, which is focusing on the perovskite solar cell. But before I go into details about the journals, I would like to have a quick introduction and a background explanation on why this perovskite solar cell is attracting my attention. So as you can see, the efficiency and stability of the solar cell is actually improved from the DSSE to perovskite. So as of June 2018, this power conversion efficiency is even improved to about 23%. However, the operation methods for this device is still relatively new, so there's still a lot of improvement for the researcher to look into the details, especially on the basic chemistry and physics of this structure itself. So from the previous slide, we learned that a planar PSC is actually the one with the highest power conversion efficiency. So if we look at the structure of the planar PSC, actually what you can see at the bottom right image here is actually consists of two different types. One is the conventional and one is the inverted. So the difference between these two structures is actually on the whole transport layer and the electron transport layer arrangement. So the most commonly used HDL is actually the spiral OMETAC or the paired PSS. While for the electron transport layer, the function is actually for the electron collection and transportation, so that the light absorbed from the transparent conducting oxide will be transferred to the corresponding electrodes. The most commonly used ETL in PSC is actually TiO2 and SnO2. So the advantages of the TiO2 is as listed here. It shows a very excellent transparency, carrier separation ability, very high electron mobility, environment stability, controllability, and also low cost. While for the advantage of SnO2 is that it has a very good contact with the perovskite layer. Also the good band edge nearby the perovskite absorber, high electron mobility, and low temperature processability. So even the perovskite solar cell show a very good power conversion efficiency, but because this technology is relatively new, so there are still a lot of drawback, which is the major challenge to the researcher to make this PSC widely used. So the major drawback include incomplete match band alignment of TiO2 with the perovskite layer, and limit conductivity of the TiO2, which lead to accumulation of the electron in the interface. So this will eventually limit the PCE and the stability of the device itself. Another thing is actually TiO2 requires a very high annealing temperature, which is around above 500 degree Celsius. So this annealing temperature is actually too complex for processability. While if let's say we lower down the annealing temperature, it will eventually deteriorate the quality of the TiO2, and consequence is the poor device performance. So lastly, the drawback is that the surface trap state, which present at the interface of SnO2 with the perovskite layer, will causing unwanted recombination to happen. So at this moment, the researchers are very active to focus to understand and optimizing the energy level and the interaction of different material at this interface, so that they can improve the performance of the device itself. So this is why I am looking into the 3 journals where the research are focusing on how we can optimize the ETL or even remove the ETL to further enhance the performance of the device. So as mentioned, the main objective of the 3 journals is actually to observe how modifying the ETLs, so either by co-dope the TiO2 or alter the ETLs into triple cascade layer, or even remove the ETL by fabricating the PSC on RBF modified plastic substrate, can reduce the electron hole recombination rate and hence increase the PSC efficiency. So all 3 researchers is actually focusing in the same PSC structure, which is the planar NIP structure as what I showed in previous slide. So here is the journal list that I have been selected. So the first journal is the efficient rare earth cold TiO2 electron transport layer for high performance perovskite solar cell. Second one is the improving electron extraction ability and suppressing recombination of planar perovskite solar cell with the triple cascade electron transporting layer. And lastly, the RBF modified FTO electrode enable energy level matching for efficient electron transport layer free perovskite solar cell. So for journal 1, actually this is the structure of how they carry out the samples. So as you can see here, the FTO substrate is followed by a TiO2, which co-doped with SM and EU, then followed by the perovskite layer, HTL, and lastly the AU electrode. So as a summary of the journal, actually the rare earth elements are being selected as co-dopant because of their capability in increasing the Fermi level. So this journal is actually focusing in co-doping instead of a single doping. This is because of few benefits such as carrier mobility, enhancing optical conversion ability, effective energy transfer process, etc. So this SM and EU co-doped TiO2 are explored and fabricated by applying PLD techniques. And the purpose of EU is to increase the UV light utilization and protect the degradation of perovskite layer from UV light, while SM is purpose for enhance the down conversion ability of EU by broadening the excitation wavelength range. So for the research methodology, it is quite standardized for how the researcher prepare the PSC device. Usually they will start up with preparing the perovskite layer, then after that preparation of the ETL and deposition of the ETL, then lastly deposition of the HTL and electrodes. So this slide here is mainly show the step on how the perovskite layer is being prepared. So first of all, the materials need to be purchased, then it will mix a certain chemistry together to create the powder, and then dry the final powder in the vacuum drying oven to prepare the perovskite powder. After the perovskite layer is being prepared, it will be followed by synthesis of the RE-doped TiO2 powder by an improved soil gel method. So they will prepare a solution A, and then they will stir it in the room temperature, and then followed by preparing solution B by adding in additional EU and SM chemistry into the solution A that prepared earlier. Then after that, they will stir this solution for quite a period of time, and then vacuum dry it, anneal it, then sinter the powder, then only that cold press it into the target that we are going to deposit later. After the target has been prepared, it will follow by a step where the researchers start to prepare a high quality film by PLD technology. So before they can proceed with the deposition, the FDO substrate need to be clean, dry, and also spin coat with a certain chemistry and sinter. Then only proceed with the deposition of the TiO2 ETL. So few samples is being prepared in the experiment. So as you can see, there's 5 different combination, where the first one is only TiO2 itself, and the second sample is prepared with a TiO2 with a EU dope, which is 1% concentration, and the third sample is TiO2 with combination of EU in 1% concentration and SM with 0.5% concentration. The fourth sample is followed by a same combination. It's just that the SM concentration being revised to 0.8%. Lastly, sample is prepared with the SM concentration of 1%. So last step of the sample preparation is actually the PSC device fabrication. Once the ETL is being deposited, it will eventually follow by the deposition of the perovskite layer, HTL layer, and also the AU electrode. So for the result and discussion part, I will separate into 2 sessions. One is talking about the structure and morphology, and another one is talking about the device performance, which focusing on the PCE, fill factor, etc. So about the structure and morphology, as what you can see in the slide here on the image, the energy band diagram is actually being measured. So the UPS spectra is also being captured, and it shows a result of Fermi level of 94.69 eV for a bare TiO2 and nearly 4.11 eV for a cold-doped TiO2. So this actually tells us that the Re ion is having higher binding affinity than oxygen ion. So this eventually lead to reduction of oxygen ions and introduction of vacancy on the surface of cold-doped TiO2 ETLs. So another result you can see from this image is that the energy band diagram show a very good band alignment for the cold-doped TiO2, which able to improve the carrier injection from the perovskite to ETL and result in higher VOC. This slide here is actually showing the cross-sectional SEM image of the sample itself. So from the SEM image, you can see every layer is uniform deposited. And another measurement done is the thickness of each layer. So as you can see on the table here, the cold-doped ETL is 40 nanometer. The perovskite layer is 400 nanometer, and the HTL is 200 nanometer, and the electrode is 100 nanometer. To understand the crystallinity of the structure itself, XRD has been carried out. So this result indicate that the structure itself is well crystalline without any impurities, and the main diffraction peaks occurs on 101, 004, 200 crystal planes. So the right parts of the figure here is actually showing the 101 peak gradually shift to a lower degree with an increased concentration of SM. So this actually indicates that the corresponding lattice expand. To understand the electron extraction behavior, IV curve measurement has been carried out. So as you can see from the figure here, the researcher applied a voltage from -2 to 2 volt. So from the figure, you can also observe that a very linear IV relationship is being measured up. So this indicates no Shakti contact was formed. Also, the doped TiO2 exhibit a higher conductivity than the one without doping, indicating a very good capability of electron extraction of doped TiO2. Besides that, you can also extract the information that the conductivity increased with the increase of doping concentration of the SM ion. So this indicates that the Re ion can reduce the defect density with optimized concentration. However, if you compare the ETL with 1% concentration of FM with the one with 0.8% concentration, the difference is not significant because the excess Re ion will eventually scattering around and will not increase the conductivity further. So since from the previous characterization, we already aware about the 0.8% concentration SM ETL will provide the best performance compared to the others. The coming characterization will all focusing on this ETL itself. So as you can see, the top view SEM image here, a very homogeneous layer is formed on this ETL, and the EDS mapping also show the existence of TI, O, SM, and EU. If we further zoom in into the top view SEM image, actually you can also see that the grain size increase with the introduction of RE. So figure A actually indicate the one without doping. Figure B show the one with only EU without SM and a grain size of 150 nanometer. And figure C is the one with EU and SM with 0.8% concentration, which show a grain size of 250 nanometer. So this increase of grain size actually showing that the improved conductivity of the device. Comparing the thin film quality with the dope and without dope TiO2, actually a very small RMS value is observed on the cold dope. So this showing that the cold dope TiO2 ETLs have a better thin film quality compared to the one without doping. Another characterization, which is the PL spectrum, also show a PL quenching after doping of 1% of EU. So the spectrum become broader and broader with the increase of SM doping concentration. So this also match with what we observed in the previous characterization, that introduction of Re ions is able to enhance the electron collection and transport efficiency. At the very beginning of the journal, the researcher also make a hypothesis that the SM ion will eventually have ability to utilize ultraviolet light and turn it into visible light. So this characterization here is also proven that this hypothesis is true, where you can see the one with SM 0.8% concentration ETL exhibit faster non-radiative transition. So this indicates the energy absorbed by SM ion is efficiently transferred to the EU ion. We are done with the characterization on the morphology and the structure of the device. So now we are focusing into the device performance in terms of PCE, JSC, VOC, and FF. So sample A to E is being investigated. So as you can see, sample D is the one we talk about, which coming with 0.8% SM concentration. So this show best performance in terms of PCE, JSC, VOC, and FF. So this finding also indicate a very excellent charge extraction and collection ability, also the better band energy alignment to perovskite layer of this ETL. In terms of IPCE, incident photon to current efficiency, the one with 0.8% concentration ETLs demonstrate the highest IPCE over the range from 400 to 800 nanometer. So the IPCE is also obviously increased between 400 to 440 nanometer because of the cooperation of SM and EU ion. So this actually effectively increase the utilization of ultraviolet light and convert it into usable visible light. So again, this is matched with what we find out from the previous characterization. Now we are moving toward the Journal 2, improving electron extraction ability and suppressing recombination of planar perovskite solar cell with a triple cascade electron transporting layer. So as you can see from the figure here, instead of one layer of TiO2, this research actually focused in a triple cascade ETL layer where it combined TiO2, SnO2, and PCBM. From all the past research, actually, most of the researcher is focusing on the double layer ETL. So for this journal, to achieve full potential of the ETL, they have investigated into a triple cascade ETL by combining the TiO2, SnO2, and PCBM. Because SnO2 is believed to exhibit a very good contact with the perovskite layer, a very good band edge nearby the perovskite absorber, high electron mobility, and low temperature processability, while the PCBM is a very good acceptor in organic solar cell. So this can effectively promote charge transfer, and also it can be served as a water resistant layer to protect the thin film against the damage of moisture. So this experiment is carried out by comparing the performance of this triple cascade ETL with the one with only PCBM or the one with SnO2 and PCBM film. The research methodology is quite similar to the first journal, where they start to purchase the material, prepare the FTO substrate, and deposit the ETL. It's just that for this research, they prepare 6 samples by combining a different material into a triple cascade ETL. So first one is the one with bare TiO2, and the second one is TiO2 combined with SnO2. The third one is only SnO2. The fourth one is TiO2 combined with the PCBM. The fifth one is the TiO2 SnO2 PCBM, which is the one we are talking about, the triple cascade ETL. And the last one is the SnO2 and PCBM combination. So after they have this ETL deposit, they will deposit the perovskite layer, HDL layer, followed by the AU electron. So same here, I will go into the structure and morphology of the journal itself, and later we'll go into the device performance characterization. So from this slide, you can see actually even though with a 3-layer combination, the energy band diagram is still showing that this 3-layer is suitable for the transport of electron because the gap between a band to band is very small. From the AFM, actually we learned that with the introduction of PCBM into the ETL, it is even better to improve the flatness of the ETL. So this result also proved that by combining 3 layers, the ETL surface morphology is still well modified into a smooth surface and able to achieve an enhanced device performance. From the light transmittance spectrum, actually all the film show obvious oscillation peaks because of the light interference effect. However, you can clearly see here with the introduction of PCBM, the light transmittance of the ETL below 400 nanometer is quite low compared to the one without the PCBM. So this is being caused by the parasitic absorption of the PCBM itself, and this parasitic absorption phenomenon is actually harmful to the device performance. After we learned from the previous characterizations that the thin film with the PCBM is actually having a better light transmittance compared to the one without. So we zoom in into the three samples that with the PCBM. But from the light absorption spectroscopy, we can see that different ETL actually did not show a very significant light absorptions. So coming to the device performance, comparing the one with PCBM and the one without PCBM, actually the one with PCBM show a better PCE, which is 13.73%. So this finding actually indicates that PCBM is still able to promote the electron transfer, smoothen the ETL surface, and benefit the following perovskite deposition. So it can be confirmed that even though the PCBM showed the parasitic absorption in the previous characterization, it's still having a positive effect on the electrical performance of the device. So among all the three samples with PCBM, the one with triple layer is actually showing the best performance. Coming to the IPCE, we do observe there is some discrepancy, as you can see, between the range from 360 to 410 nanometer and 500 to 600 nanometer. So the reason of this discrepancy actually caused by the trap state which present in the perovskite film. Even though we do observe this discrepancy, the cell B, the one with triple layer PCBM ETL, still demonstrate a very high integrate current density compared to other two samples. Because of the discrepancy observed in the IPCE spectrum just now, the researcher tried to focus in the three samples that with PCBM to evaluate whether their performance from other perspective is still suitable to be used as an alternative for ETL. So the first thing they look into is the top view SAM image, and all the three images show a tightly arranged crystalline grain. The figure A actually is the one without SNO2. So even though the crystal structure show no pinhole over the whole scan area, but the grain size is non-uniform. So you can see there's a large number of small grain and larger grains that intersect with each other. So figure C actually show the one with SNO2 but without DiO2. So this one is actually show a better arranged crystalline grain. And also indicating that the SNO2 layer able to compensate the disadvantage of DiO2 information of perovskite film. So this will also improve the conductivity eventually. So if let's say I combine DiO2, SNO2 and PCBM in figure B, the grain size is very consistent, where there's a higher number of large crystalline grain compared to the other two. So this indicates that the triple cascade ETL is helpful in crystallizing high quality perovskite material. To further confirm that the SRD is actually being carried out, so you can see from here these three samples is actually well crystalline without any impurity, and the main diffraction peaks occurs on 110, 220 and 310 crystal plane. So the one with triple layer ETL has the smallest full wave half max comparing to the SNO2 PCBM ETL, which has the largest full wave half max. So this actually indicates a larger grain size for this triple layer ETL is consistent with the SAM image measurement. From the PL measurement, actually the PL quenching phenomenon is observed in the triple layer ETL. So this actually indicates that this triple layer ETL with DiO2 and SNO2 is actually given the best charge transfer and transport ability compared to the other two. But the PL quenching is also not able to tell whether the performance is actually coming from a better charge transfer or is it led by the recombination center. So if let's say it's led by the recombination center, it actually is not preferable for the device performance. That's the reason why the TPRL is being further investigated. So from this diagram, actually the TPRL intensity of DiO2, SNO2, PCBM ETL is decay faster compared to the other samples. So this actually indicates the best suppressed trap acid recombination between the ETL and the perovskite, which will benefit the device performance. So come to the last journal, which is the RBF modified FDO electrode enable energy level matching for efficient electron transport layer free perovskite solar cell. So from this journal, actually you can see the ETL as what I talked about in the journal 1 and 2 is totally being removed, and it is replaced with a very thin coating of RBF on the FTO substrate, and then it will directly followed by the deposition of the perovskite layer. So the researcher from this journal actually believe that by remove the ETL from the PSD structure and grow the perovskite layer on the FTO substrate directly without go through a high temperature process TiO2 ETL will be benefits from the ambipolar charge transport merit of the perovskite film itself. So this is the reason why a water-soluble rubidium fluoride is being coated on top of the FTO to modify the Fermi level. The research also claimed that the RBF able to eliminate the electron transport barrier and greatly increase the efficiency of the electron transport and extraction. It also able to block the injections of hole and suppress electron-hole recombination, reduce the surface roughness of the FTO, and at the same time improve the wettability of the FTO surface, which lead to better interfacial contact with perovskite film. The research methodology for this journal is slightly different compared to the other two journals that I have presented because for this journal it don't have to prepare the ETL layer, whereby they only need to prepare a pattern FTO glasses for a better coating of the RBF layer. Once the pattern FTO glasses has been prepared, they will spin coat the RBF on this FTO substrate. So they will try to stir this solution in a magnetic stirrer and then filter the solution before they spin coat it. So after they spin coat, they will need to heat it for a certain degree Celsius and transfer this substrate to a dry air glove box to deposit the underlying perovskite layer. So now you obtain a FTO substrate coated with RBF and also with a perovskite layer on top of it. It will be followed by the deposition of the HTL and AU electrodes. So from the AFM result, it shows that the one with the RBF coating is actually having a better thin film quality compared to the one without. The same image here actually showing that even coated with the RBF, the grain size or the grain structures is not impacted with the coating. So on the right side, actually the figure show the EDS mapping. So you can clearly see that the RB elements are uniformly distributed over the FTO substrate. So to understand how well the perovskite layer is being deposited on the FTO substrate without the ETL layer, wettability test is being carried out. So the result actually show that RBF layer exhibit a superior hydrophilicity and allowing a complete coverage of the perovskite precursor solution on the FTO substrate. So this is very beneficial to form a uniform and high quality perovskite film. The energy band diagram actually shows that the one with RBF coated thin film, there is an oriented dipole formed at the FTO perovskite interface where the dipole moment is direct outward from the FTO and suppressing the electron-hole recombination. The hypothesis that RBF coated thin film able to improve the charge transport and extraction is again being proven by the PL quenching phenomenon that observed at the coated RBF thin film. So this actually caused by the faster charge transport within the perovskite layer, and eventually it will enhance the device performance. And another characterization, which is the TPRL, actually also shows that the photoluminance decay of the perovskite with RBF coating is faster than the one without. So this is telling us that the RBF interlayer can regulate the charge carrier injection behavior between the perovskite layer and the FTO electrode. To further investigate the device performance with and without RBF, a few samples are being prepared by the researcher. One is totally without RBF, another few samples is with increased concentration of RBF. So you can see from the table here, the one without RBF is with the lowest PCE, which is 16.03, while the one with 2.5 mg per milliliter concentration of RBF showing the best performance of PCE, which is 18.79. So further increasing the concentration is actually not helping in further improve the PCE, because excessive thickness of the RBF will eventually increase the resistance of the device. So this result actually telling us that the RBF can actually improve the device performance. Looking into the IPCE, both coated and without coated with RBF show a same or the similar spectrum where both are relatively flat. But if you look at the integrated current density, the one with coated RBF definitely showing a better current density, which is 19.86, compared to the one without, which is only 19.09. So now we are about to conclude what we have learned from the three journals. So from the first journal, actually we learned that the cold-up TiO2 with Re ions actually show a very advantage in charge extraction and collection. So this is contributed by the effective energy transfer between the both Re ions. So it actually effectively increased the utilization of UV light and convert it into a usable visible light. So from journal 2, we learned that the triple cascade ETL actually is very effective in suppress the recombination. However, from the IPCE, we also learned that there's a potential of parasitic absorption phenomena caused by the PCBM. So this will eventually be a disadvantage if come to a mass production. So for the last journal, we learned that the issue of energy level mismatch actually able to be resolved if, let's say, we remove the ETL. So by adding in the RBF coating layer, this will be eventually improved, where the interface dipoles will form, and thus it can demonstrate a downward energy band bending and eliminate the electron transport barrier. So this will eventually improve the electron transport and extraction efficiency. Putting all three journals into comparison in terms of architecture, you can see that compared to the conventional structure, all three journals is trying to modify and play around with the ETL layer. So the first journal is actually doping SM and EU ion into the TiO2. The second journal is actually adding in the SNO2 and PCBM layer to form a triple cascade layer. And the last journal is actually removing the whole ETL and only coat RBF layer on the FTO substrate. So all the three journals is actually go through a similar preparation and the methodology, whereby they have to etch the FTO substrate and then followed by the deposition of the ETL material, and then lastly followed by the deposition of perovskite layer HTL and also the metal anode layer to form a final PSC device. Comparing the device performance, actually the sample from journal 1, which is the one cold-up TiO2 with SM and EU ion, actually show a best performance in terms of PCE compared to another two. However, the difference between the three journals is actually not very significant. Talking about the IPCE, so actually from the journal 1 and journal 3 also show a relatively flat spectra. Only the journal 2 itself show a discrepancy in the spectral. Talking about the novelty of each journal, the first journal is actually looking into the cold-up TiO2, whereby the past research is only focusing on single doping. So the result from this journal actually showing that the energy transfer is being improved compare the cold-up TiO2 with the single doping. So the cold-up ETL is also proven that able to prevent the degradation of the device from UV light. The second journal, even though the SNO2 has been commonly used as an alternative of TiO2 as ETL, but no research has been looked into the combination of TiO2, SNO2, and PCBM into one structure. So this research actually look into a triple layer ETL instead of double layer ETL, and the result is showing that the introduction of the PCBM actually able to improve the flatness of the FTO substrate, and even though with a three layer cascade, the electron transport and extraction is still being able to be improved. So the last journal actually is the most challenging one, because the researcher have to remove the ETL totally from the conventional PSC structure. So this concept is very new and very challenging in terms of the researcher have to create a very smooth and even FTO perovskite interface. So this journal addressed this issue very well by coating the RBF on the FTO substrate. After looking into all the comparison, actually journal 3 showed the best novelty by removing the ETL from the conventional planar PSC structure. The experiment result is very promising, where they're able to demonstrate a downward energy band bending at the FTO perovskite interface and totally remove the electron transport barrier. So this actually resolved the issue of energy level mismatch that encountered by other conventional planar PSC. So As a result, the electron transport and extraction efficiency is very well improved, and by introduction of this IBF coated, the charge recombination at the electron and perovskite interface is also being reduced. Besides all this benefit, the sample also demonstrates a better interface contact with perovskite layer after coated with IBF. So removing the ETL is actually very beneficial in reduce the potential risk of lattice mismatch between the FDO to ETL and the ETL to perovskite interface. Also, they're able to reduce the potential of occurrence of impurities in between all these interface. So in terms of fabrication, removing one ETL from the structure itself definitely able to reduce the process complexity and also increase the reproducibility. With all the summary and the conclusion have been made, here I would like to end my presentation about this project, and thank you for your attention.